Hi, this is lesson 6 and it's the last part of equations in motion. This one is going to be looking at special graphs that you need to know. So first of all, there's a starter task, and if you pause the video at the moment and have a go at these. Okay, this should not by now be very familiar to you, especially the first part, calculating the total displacement. The first thing we do is we get the area under the graph. We've got 4 areas here. Broadly speaking, we've got area 1, which is this triangle here, area 2, which is this rectangle here, area 3, this triangle here, and area 4, this triangle at the bottom. If we add them together, I'm not going to go through this in great detail, but we get this sum here, and we should get a final answer of 5 meters. The only slight complication here is that the last area, the area under here between 4 and 5 seconds, is minus 1 meters, which remember just means 1 meter in an opposite direction. Okay, sketching the corresponding acceleration time graph. Well, again, going back to previous lessons, and in fact back to National 5 as well, acceleration is given by the gradient of the graph. There are 3 sections to this graph. We've got the first section between 0 to 1 seconds, and the acceleration here, if you work it out, is 2 meters per second squared. The second section is between 1 and 3 seconds, where you should be able to see that there's no acceleration whatsoever, so it's 0 meters per second squared. And the third section is between 3 and 5 seconds. Now, although this goes from a positive to a negative velocity, the acceleration is constant, and it's negative 2 meters per second squared. That gives this graph here, which looks a bit strange, a bit blocky, but that's the way the acceleration time graphs will look at higher level. And hopefully you can see this corresponds to the numbers on the left. Again, the vertical lines here, in a sense, I suppose you could miss them out, but they're basically just showing that the acceleration is changing almost instantaneously. Okay, our learning intentions for today, we're learning to interpret 2 very important velocity time graphs. The first one is for an object that's thrown into the air and falls back down, so if you just throw something back up, throw something up in the air and catch it again at the same height, and a bouncing ball. Okay, the first situation we've got here is the object thrown into the air and falling back down. Now, either of these graphs could actually represent that motion, right? The reason we've got them different way around is because it depends which way you decide is up. If you decide that up is positive, then up is negative, then this first graph will be the right one, and if you decide that up is positive, then the second graph is the right one. And I think there's a bit of confusion sometimes in terms of, well, how do you decide whether up or down is positive? It doesn't actually matter. The thing is, the graphs are there to represent the motion, and the negatives and positives are there just to represent a direction. Okay, it might seem a bit abstract, a bit strange, but as long as you stick with whatever you choose at the beginning of a question, the beginning of a problem, as long as you stick with it all the way through, it will give you the correct answer, the correct results at the end. And scientists and engineers, physicists use this all the time. It's basically just a way of putting directions into numerical form so that you can use equations and graphs and such like to solve them. Don't worry about it too much. Okay, so this is the case when the ball moves up at the start, so up is negative. So the things that we need to recognise in this graph, first of all, we need to recognise that this graph is in fact something being thrown up in the air and falling down, no matter which way it's oriented. In this case though, up is negative, so everything below the axis is negative velocity. At this point here, at 2 seconds, the velocity is 0. For an instant, it's 0. And this is right at the top of the throw. There is still an acceleration, as I've mentioned in previous lessons, but because the acceleration doesn't actually change, the acceleration is constant here. But basically at the top of the throw, it is 0. It's at highest point. So it's not moving upwards, and it hasn't quite started moving downwards yet. At this, the top part of the graph here, the ball's basically now moving downwards, so we've got a positive velocity. What about the acceleration? Well, the acceleration is the gradient of the graph, and the gradient is actually constant throughout this entire graph. It's a straight line. The gradient is positive, and because positive is downwards, which is the direction of acceleration, that basically works out. You would expect something to be accelerating down the way. And this is why we've got to be careful when we're using speeding up and slowing down. What's actually happening here is the speed, as you throw an object up in the air, it slows down and then it speeds up. But the acceleration is in a constant direction. And that makes sense because gravity, or the force due to gravity, is always pulling down the way. Weight is always pulling down the way, and it's always causing a downward acceleration. This is basically the same thing with the graph the other way around. So in this case, the ball's moving upwards, and we've decided that up is positive, so it starts off with a positive velocity. It reaches a maximum height where the velocity is 0, and then it starts moving downwards, which is a negative velocity. So the velocity is increasing in a negative direction. The acceleration is still the gradient, and the gradient is still constant. It's a straight line. The gradient is negative. And because in this case negative is downwards and the direction of the acceleration is downwards, then it still all works out. The next case that we have to look at is the bouncing ball. In this case we've got a ball that's dropped, and this is a velocity time graph for that ball. It looks horrendously complicated, but actually we can break this down. There's three things you really need to know about this. The first step you have to look at is which direction is positive. Normally there's a clue about this in the question. Sometimes if it says the words the ball is dropped, then the first movement, if you drop something, is always going to be downwards. So if the movement is downwards, then that means in this case O to P here is positive. So that means that positive is downwards. So everything above the axis is basically moving downwards, and everything below the axis is the ball moving upwards. And that I'd actually put these circles on if you're trying to work this out, because it helps keep you in the right direction. Step 2 is to identify the highest points in the bounce. Well, actually very similar to what we had before. The highest points are where the velocity is 0, but you've got to be a wee bit careful. So that's a high point, that's a high point, and that's a high point. However, that is not, and we'll explain why. We'll explain what's happening here. There's a couple of points of this. There's that point there, and that point there. These are not high points, and we're going to explain what's happening in these sections in the next slide. Okay, now we've established which way is downwards and which way is upwards. So positive above the axis is downwards, below the axis is negative and is upwards. So the next thing we need to do is we need to identify where it hits the ground. So when it bounces, the velocity changes from a very high positive value to a very high negative value. So this basically happens between P and Q, and between S and the bit at the bottom here, and this unknown point here, and this unknown point down here. So these are the points where basically it's actually bouncing, it's rebounding. It hits the ground at P, S, and this point here. Now the reason that these middle points here, even though the velocity is 0, are not the highest points is because they're in the middle of this rebounding section. The rebounding section is always pretty close to a vertical line. The size of the acceleration is absolutely enormous. When you let a bouncy ball go and it bounces off the ground, it changes direction very, very quickly. It has a very high change in velocity in a very, very short period of time. So it has a very, very large acceleration. Okay, in summary, the ball's dropped between 0 seconds and P. it accelerates downwards. Its downward velocity increases. Secondly, it hits the ground at point P, and its velocity rapidly changes from a high downwards velocity at P to a high upwards velocity at Q. From Q to R, the ball is moving upwards, and the magnitude size of its velocity decreases to 0. At R, it's at its maximum height, and it has a velocity of 0. And from R to S, it's moving downwards again. It's got a positive velocity, and its velocity increases in a downwards direction. Now, there's a lot of words there, and I've complicated it even more by using the word magnitude. Now, there are a few things in physics that you really, by the time you get to higher physics, you can't really get around them. You must use the word magnitude, right, where it's appropriate. The reason for that is that if you're basically talking about a velocity, let's say this is negative 3 meters per second here, and let's say it's 0 here, right? Is that actually increasing? Well, speed is definitely decreasing. It's going up the way, and it's slowing down to 0. I don't know. I mean, arguably you could say it's increasing because it's going from negative 3 to 0. But this is where you get into all sorts of difficulty. So if I talk about magnitude, then I'm basically saying the size of. And I know it's not something you use in your everyday speech, but it's really important to use it when you're talking about concepts in physics. It actually, although it makes it more complicated at first, it results in the end in actually something that is fairly clear and simplified. Right, I've got two wee last points here. One of them is about physics and one of them nothing to do with physics. The first one is just a wee question to set you. Why does the size of the peak velocity at, which is basically at P and S, so the highest velocity, decrease each time? It does it both on the positive side at P, S and here, and also on the negative side, Q, there and there. But I'm going to leave you to think about it. I won't give you an answer at the moment. You can maybe put in a comment in Google Classroom if you think you know the answer. Otherwise, we'll talk about it when we get back to school. Number 2, and this is absolutely nothing to do with the actual physics of the situation, but I think it's probably a general thing for an awful lot of physics. Physics is taken as being quite a hard subject, and I wouldn't totally disagree with that. But the thing is that you have to, there's a lot of concepts here that are quite abstract or can be quite confusing. If you look at all of them in one go, if you tried to basically go through a complete PowerPoint or a complete lesson in one go and never went back to it, then you will get confused. I would be confused. What you have to do is you have to look at them a little bit at a time, maybe one slide at a time, have a look at the videos, pause them, replay them, pause them, replay them, and try and really understand what's going on. Make notes. Then come back to them later on, read it, digest it, reread it, redigest it until you understand. And then you can basically have a go at practicing it. Do some of the questions. If you don't understand the questions, you're not sure how to do it, you go back to the slides again. It's about going back and forward. This is basically what you have to do to learn at home. This is not easy stuff, but if you can learn this at the moment, then it's going to make a big difference to your physics when you come back. It really will. You can basically get this so you're absolutely solid with it, and it will make your life a lot easier, and it will really, really increase your understanding. But it does take some time. Okay, right, now try the questions after this, and I'll see you in the next lesson.